We're now going to have a look at how we can describe quantitatively what's happening with the energy that we add during phase changes or during changes of state. So when we've already mentioned that when we melt a solid, although we're adding heat, we're not actually increasing the temperature. All that's happening is that the potential energy of the particles is increasing, and we're not changing the random kinetic energy of the particles. So we're going to focus on describing this numerically now using a concept called latent heat. And the word latent in this sense means hidden. So our objectives are to define specific latent heat or latent heat, and then we'll go through a couple of examples of how you can apply this concept to solving problems. Alright, so latent heat. When we add heat to a solid, for example, at its melting point, so if we have ice, for example, at 273 Kelvin or 0 Celsius, the heat that we add will cause fusion or melting, but there will be no change in temperature. So we're adding heat to this ice, and what we end up with is water at the same temperature. So if we start off with ice at 0 degrees and we add heat, we'll end up with water at 0 degrees. The heat that is required per kilogram to change a solid to a liquid is called the latent heat of fusion. So the latent heat of fusion is the heat that we need to add per kilogram to change, for example, ice at 0 degrees to water at 0 degrees. The heat that is required per kilogram to change a liquid to a gas is called the latent heat of vaporization. So in this case, if we want to change 1 kilogram of a liquid water to 1 kilogram of water vapor, then we need to add what is called the latent heat of vaporization. So the latent heat depends on a couple of things. Firstly, it depends on which phase change we're going to undergo. So if fusion and vaporization, the latent heats in these two processes are different. And the second thing it depends on is the substance. So water has a latent heat of fusion of about 333,000 joules per kilogram, or 3.33 kilojoules per kilogram. Sorry, 3.33 times 10 to the 5 joules per kilogram. Water has a latent heat of vaporization of 2.26 times 10 to the 6 joules per kilogram. So these are both water. These are the two different types of latent heat for water, and you can see that much more is required to convert, much more energy, much more heat needs to be added if we are to vaporize a kilogram of water than if we are to melt a kilogram of water. Gold has a latent heat of fusion of 6.44 times 10 to the 4 joules per kilogram. So changing 1 kilogram of gold, solid gold, to 1 kilogram of liquid gold takes less energy than changing 1 kilogram of ice to 1 kilogram of liquid water. The equation that we use to work with latent heat is given by this equation here. It's Q is equal to mL. So Q is the amount of heat that we add, M is the mass, and L is the latent heat of vaporization. So this equation determines how much heat we need to add during the changes of state. So L here is either the latent heat of fusion or the latent heat of vaporization, depending on which process we're dealing with. And what we'll do now is we'll work with this equation to solve some problems. Alright, so a 25 gram ice cube at negative 10 degrees Celsius is dropped into a glass containing 300 grams of water at 20 degrees Celsius. Find the final temperature. Okay, and we're given the specific heat capacity of ice and latent heat of fusion, and we need the one of water, which is 4,200 joules per kilogram per Kelvin. Alright, so in order to solve this, we start with the same principle that we've used before, which is that the heat gained by the ice cube is equal to the heat lost by the water. However, because in this case the ice cube is going to melt, we need to take into account the latent heat of the ice as well. And so, and then the fact that the ice is going to reach some final temperature, it's going to have to increase as water as well for a little bit. Okay, so what is the heat gained by the ice? So that's going to be the MC delta T ice plus ML fusion plus MC delta T water. And that's going to be equal to the heat lost by the water, which is negative MC delta T. Okay, so what happens to the ice is that it first heats up to 0 degrees, which is what this first part is here. And then it changes from solid to liquid, so we need to add heat to make that happen. And then it's going to increase to some equilibrium temperature, which is when no heat will flow anymore, when the temperature of the melted ice is equal to the temperature of the water. Okay, so let's figure out what all this stuff is. So we start off with 25 grams of ice, so that's 0.025, this is going to become a long equation, times the specific heat capacity of ice, so times 2,200. That's not a decimal point, that's a mistake. Just fix this up. Which is 2,200 times the change in temperature of the ice, which is, well, it remains at ice until it gets to 0 degrees. And so that's going to be the final minus the initial. The final is 0 minus the initial, which is negative 10. Plus the mass of ice, which is 0.025, times the latent heat of ice of fusion, which is 334,000, plus MC delta T of water, which is 0.025 times the specific heat capacity of water, which is 4,200. I don't know why that became so messy. Let's just rub that out, fix it up. Times 4,200 times TF, which is what we're trying to find, minus T initial, which was 0, right? Okay, so that's our left-hand side of our equation. That must be equal to, the mass of water, which is 0.3, times the specific heat capacity of water, which is 4,200. In fact, this is a loss, so this should all be negative. Times the change in temperature of the water, which is TF, minus the initial temperature of the water, which was 20 degrees. Okay, and so now we have this large nightmare of an equation. We need to simplify it down. So these two terms, we can just work out what they are. And then this one, we need to keep it as an unknown in it. And so it's just going to be, well, let's just work out what all the individual bits are. Okay. The first term on the left, which is 0.025 times 2200 times 10, is 550. Oops. 550 plus. And then this middle term is 0.025 times 334000, which is 8350, plus, let's multiply out what comes before the bracket there. So that's 0.025 times 4200, which is 105, times TF minus 0, so that's just TF. Okay, and that must be equal to, so what's that, negative 0.3 times 4200, which is 1260, times TF minus 20. Sorry, that's negative. Times TF minus 20. Okay, now this is looking a bit more reasonable. So our last step here is going to be to find TF. So if we just multiply out the bracket on the right hand side here, we're going to get here is going to be equal to negative 1260 TF minus, sorry, not minus, plus, because it's a negative times a negative, 25,200. Okay, now we move all the TFs over to the left and all the numbers over to the right, and we get 1365 TF is equal to 16,300 . So TF is equal to 11.94 degrees. In fact, we only wanted to 3 significant figures, so we can just say that it's 11.9 degrees. C. How much energy does a freezer have to remove from 1.5 kilograms of water at 20 degrees to make it ice at negative 12 degrees? Okay, so we want to figure out what the change in heat is, what the heat loss is, and there's going to be 3 steps to this process. We have cooling down of water from 20 to 0, so MC delta T of water, and then we have the fusion of the water, or the freezing of the water, so that's plus ML, and then the cooling down of the ice to negative 12 degrees, that's MC delta T ice. And so what we have here is 1.5 kilograms. 1.5 kilograms. The heat capacity of water, specific heat capacity of water is 4,200 times the final temperature, which is 0 minus 20, because it started off at 20 degrees. And then we have to add to that the heat that we need to remove to turn the water into ice, which is 1.5 times the latent heat of fusion of ice, which is 334,000. And then we have to add to that the heat required to cool the ice, which is mc delta T of ice, which is 1.5 times C of ice. The specific heat capacity of ice is 2,200 times the change in temperature of the ice, which is the final minus the initial temperature, which is negative 12 minus 0. In fact, this should be, because we're removing heat, we're actually taking heat away there as well. And so the change in heat required, so that when we're freezing water, we're actually taking away the latent heat, not adding it. And so we're going to have a negative energy for that as well. Okay, so what do we end up with here? We end up with negative 126,000 for the first stage, and then minus 1.5 times 334,000, which is 501,000. And then we need to take away this last little bit here as well, which is 39,600. And so the total amount of heat that we need to remove is negative 6,6,6,6,6, or we only wanted to two significant figures, so that's 6.6. Negative 6.7 times 10 to the 5 joules. And the reason it's negative is that we had to remove that much heat.